It's really common to deliver electrical power using sinusoidal or AC voltages and currents. This video introduces the basics of AC power. AC power is delivered by sinusoidal signals, and it's based on steady-state sinusoidal analysis of circuits. The first thing I'll cover is what is called instantaneous power. That's simply the power as a function of time. It's denoted as a lowercase p of t, and it's defined as the product of voltage and current at the corresponding time. AC power results from AC signals, which are sinusoidal functions of time. The voltage as a function of time will be written as V sub m times the cosine of omega t plus theta v. So the voltage has a magnitude V sub m and a phase angle theta sub v. The current is I sub m times the cosine of omega t plus theta I. The current has a magnitude I sub m and a phase angle theta sub I. Both signals have the same frequency, omega, and they both have zero average values. If I plug these signals in for V of t and I of t in this equation, apply a few trigonometric identities, and do some algebra, I can write the instantaneous power as this. This equation consists of two terms. The first, V sub m times I sub m over 2 times the cosine of theta sub v minus theta sub I, is a constant. It depends not only on the amplitudes of the voltage and the current, but also on the phase difference between them. The second term is V sub m I sub m over 2 times the cosine of 2 omega t plus the sum of theta v and theta I. This sinusoid has twice the frequency of the original voltage and current signals, an amplitude of V sub m I sub m over 2, and is shifted in time by a phase corresponding to the sums of theta sub v and theta sub I. The important information in this equation is probably easier to understand graphically. So next we'll look at a plot of this function. This is a plot of this instantaneous power function. Some of the details about this equation itself won't be terribly important to us, but there are a few features we'll need to know about. First, the average value of this function is not 0. The constant coefficient here is the average value of the function. The sinusoid is offset from 0 by V sub m I sub m over 2 times the cosine of theta sub v minus theta sub I. The sinusoidal component of the signal is superimposed over this average value. It has an amplitude of 1/2 times V sub m times I sub m. Since the cosine of theta v minus theta I is always less than or equal to 1, the sinusoid will take on negative values during parts of its cycle. Recall that when power is positive, power is being absorbed, and when power is negative, it's being generated. Changing the phase difference between voltage and current changes this average value and moves the sinusoid up or down. That means that the relative amounts of absorbed versus generated power will depend on this phase difference. Instantaneous power is not really useful from a practical standpoint. What's important is the average power being delivered over the course of a long period of time. By definition, the average of a time-varying signal over some time period is the integral of the signal over the time period of interest, say from time t0 to t0 plus capital T, divided by capital T. If we do this math to calculate the average power over one period of the cycle, this turns out to be the average power. Average power is represented as a capital P, and it's 1/2 of the product of the voltage magnitude times the current amplitude times the cosine of theta sub v minus theta sub I. This result agrees with what we saw in the previous slide when we plotted the instantaneous power. The average value on that plot was just this, so this is the average power. Average power is also called real power. Its units are watts, which is abbreviated as a capital W. When I introduced AC power, I used what appeared to be arbitrary voltage and current signals. Subsequently, I used those as if they were unrelated to one another, except that they shared the same frequency. However, when we're doing AC power calculations, the voltage and current signals are not independent. Power calculations are nearly always in the context of determining the power delivered to a load. So if we want to determine the average power delivered to this load impedance Z sub L, we have to use the voltage across the load and the current through the load in our power calculations. Always keep in mind that the voltage and the current you use in power calculations have to be consistent with the power you want to find. In particular, the voltage and current you would use to find the average power of this load would be related through the load impedance. Voltage is current times impedance. So the voltage magnitude will be the current magnitude times the magnitude of the impedance. The voltage phase angle will be the current phase angle plus the phase angle of the impedance. Now let's do an example. In this example, we want to find the average power delivered by the source in this circuit. AC power analysis implies steady-state sinusoidal analysis. So the first thing I'll do is convert the circuit to the frequency domain. This is the frequency domain circuit. To get the power delivered by the source, I need to calculate the source current, I sub S. The source current will be this voltage, 100 at an angle of 0 degrees, divided by the equivalent impedance of the circuit, which is the sum of these two impedances, 10 minus J10 ohms. This is 100 at an angle of 0 degrees over 10 root 2 at an angle of minus 45 degrees. So I sub S is equal to 10 over root 2 at an angle of 0 minus a minus 45 degrees is positive 45 degrees. The power of the source, therefore, is the voltage magnitude, which is 100, times the current magnitude, which is 10 over the square root of 2, over 2 times the cosine of the voltage phase, which is 0 degrees, minus the current phase, which is 45 degrees. This is 1,000 over 2 root 2. The cosine of negative 45 degrees is 1 over root 2. So this becomes 1,000 over 4. And the power delivered by the source is 250 watts. Now that we've got the source power, let's see how that compares to the average powers dissipated by the resistor and the capacitor. Let's find the resistor power first. To find the resistor power, we need the resistor voltage, V sub R. By Ohm's law, V sub R is I sub S times 10 ohms. So V sub R is 10 ohms times I sub S was 10 over root 2 at an angle of 45 degrees. So resistor voltage is 100 over root 2 at an angle of 45 degrees. Now the power dissipated by the resistor is going to be the voltage magnitude, 100 over root 2, times the current amplitude, which is 10 over root 2, divided by 2, times the cosine of the voltage phase is 45 degrees, minus the current phase is also 45 degrees. The cosine of 0 is 1, so this becomes 1,000 over 4, so the resistor power is equal to 250 watts. The power dissipated by the resistor is exactly the same as the average power delivered by the source. That means that the capacitor's average power has to be 0, but let's check that out. To get the capacitor power, we need the capacitor voltage, V sub C. By Ohm's law, V sub C is equal to I sub S, which is 10 over the square root of 2 at an angle of 45 degrees, times this impedance, negative J10 ohms, which is 10 at an angle of minus 90 degrees. So this is 100 over the square root of 2 at an angle of 45 minus 90 is negative 45 degrees. Power of the capacitor is going to be the magnitude of the voltage. V sub M in this case is 100 over root 2 times the magnitude of the current, which was 10 over the square root of 2, divided by 2 times the cosine of the voltage phase is negative 45 degrees, minus the current phase, which is also 45 degrees. Negative 90 degrees is the phase angle difference. The cosine of negative 90 is 0. So the capacitor average power is this times 0, which is 0 watts. Average power is used to perform non-electrical work, which means it's converted into non-electrical forms. The capacitor stores power and returns it back to the circuit. It doesn't actually dissipate any power. All of the average power provided by the source is dissipated by the resistor, where it's converted to heat and lost from the circuit. The formulas we've used in this video are in terms of the peak values or the amplitudes of the voltage and current signals. However, effective or RMS signal levels are probably more commonly used in power calculations. We'll talk about RMS levels in the next video.